So our next speaker is Dalia Patino-Echeverri. She is the Gendel Family Associate Professor of Energy Systems and Public Policy at the Nicholas School of the Environment at Duke University. She explores, assesses, and proposes technological, policy, and market approaches to pursue environmental sustainability, affordability, reliability, and resiliency in the energy sector. Most of her work focuses on the decisions regulators and private actors must make regarding capital investment and operations in the electricity industry and quantifying the value of flexibility in multiple dimensions. And this is a special treat for me because Dalia is the principal investigator on the GRACE project, which has been funded by ARPA-E since 2020. GRACE stands for A Grid That's Risk-Aware for Clean Electricity. I was fortunate enough to be brought into that team by Dalia. Kyle, many other folks at Duke and other institutions are part of that. And it's all about making vertically integrated utilities more reliable and more efficient in the face of uncertainty. So hopefully you'll also find this interesting, Sean. And Dalia, the floor is yours. Thanks so much.
Thank you, David. And hello, everyone. It's so nice to see old friends and new friends. Yes, I'm going to tell you a little bit about GRACE. GRACE is one of the 10 projects that received funds from the ARPA-E program PERFORM, which is the performance-based energy resource feedback optimization and risk management. And we were asked to focus on the Southeast since other groups were looking at other parts of the country. So we received $2.5 million for 3 years. We are on our final year, the third year. And what I can tell you is that we have already developed a power system, a scheduling and dispatch framework that is very good at considering the risk that is posed by weather-based and also intrinsic uncertainty. And this framework is computationally tractable so that it can be used now. It's not something for the future, it's for next year, hopefully. What is a scheduling and dispatch approach? It's basically a framework that tells you which power plants you need to turn on and off at any point in time, and then how much electricity you need to generate with each of these power plants hour by hour. And because there is a place, this is a place that has storage, then the question is also how to use the energy storage facilities, when and how much to charge them and discharge them so that we can have a reliable system that meets demand 24/7. So our approach minimizes operating costs. It also maintains or improves reliability. It maintains or improves the utilization of the low carbon resources, so it shouldn't increase greenhouse gas emissions or emissions of other air pollutants. And it should make the best possible use of this fantastic resource we have in some systems, like we have here in North Carolina and South Carolina, which is a pumped hydro storage facility. It's a large, long duration storage facility. Okay, so actually it's two big dams you can see on Bad Creek, and you can see the beautiful pictures there. And then the last thing our approach does is it quantifies the impacts of the grid resources on system risk. So for each asset, we would like to know, does adding this asset to the grid alleviates risk or does it create risk? And you can think pumped hydro storage alleviates risk. And renewables, they reduce emissions, but they, with their variability and uncertainty, increase risk. But how do we quantify them? There is no time to talk about all those things today, so I'll just tell you very quickly the components of this improved scheduling and dispatch system. And the first part is uncertainty characterization model, where I'll tell you more about it in a little bit. The second part is an risk-adjusted day-ahead weekly horizon unit commitment model. And it is risk-adjusted because we are considering in the objective function not just reducing their cost, but also containing the risk. And the third module of this approach is a library of solutions. We store many solutions to this optimization model and later search these solutions so that we can get the outcomes we want, which is very fast times running this optimization problem and maybe better solutions if we had a set problem. The last part is just how do we make this into an hour by hour or minute by minute decision, okay? The project has several institutions And I just show you very quickly Jim Smith. You have heard of him with the paper he just published with David. Then here at Duke, we have all of us. You can see Dimitris, Mauricio, and Sharon here, and Kyle. Then at NC State, I think it was Henry was here, and Professor Jordan Kern leading them. At Ohio State, we have Antonio Conejo. It's really like an honor to have Antonio Conejo, who has written like the best books on optimization under uncertainty in this country. And we have PNNL, and right now working very hard with us is a postdoctoral fellow, Wei Wan. Okay, so I said we have these components, right? So certainty characterization, our risk-adjusted model, solution libraries, and then a searching algorithm of these solution libraries. Where do we use machine learning or here? So module 1 is heavy on machine learning because we are characterizing uncertainty based on the weather. How do we find the relationship between weather and demand, electrical demand? How do we find the relationship between weather and solar production? How do we find the relationship between weather and the error we make in solar production prediction, and the error we made on demand prediction? And then there is other part which is like very obvious. We draw a very big neural network here for the library searching algorithm. So I'm going to tell you a little bit how that works in a second. But first, I'm going to tell you we have like 4 pieces of software. So the first one is a probabilistic forecast generator. The second one is our risk-adjusted stochastic week-ahead unit commitment model. And it has a balancing unit commitment, so it's something that works in real time. And then we have our solution library searching algorithm, which is the SOLIS. And then we have an EMS that schedules and dispatches everything. So I'm going to tell you a little bit about this probabilistic forecast generator. We have a couple of versions. One is based on the company's data, and the other one is all based on publicly available data. And we have made significant progress on the second part. What we want to do is we want to have forecasts of load and forecasts of solar production, and for the future, forecasts of wind production. And also, we want to have these forecasts not as a one point in time, a single estimate of what is going to happen, which is the forecast we traditionally use in the electricity industry. We want to have them as ensembles of possible values and their probabilities. And they have to be weather-based because the weather is the source, the main source of almost all the uncertainty. There is all this other part that we call intrinsic, which is just the inherent properties, physical properties of these solar panels that will make them disconnect or produce or underperform. But for the most part, it's weather-based, and this allows us to maintain the correlation among all the variables that we care about. So we take historical weather forecasts, we take historical weather actuals, we put them together and get the historical forecast errors. And then we find a stochastic process that characterizes weather forecast error. And we can do this with a regular ARMA model. We can also do this with a machine learning model. And then we get the weather forecast errors ensemble. And for any single point weather forecast, we can get a probabilistic weather forecast. And probabilistic is what we want. We want probabilities of things happening, and we want all the things that could happen to be considered. And then we have load and solar production models. So for each of these, we're going to input how do we feed these models? These are all machine learning models. So the load model, for example, it takes historical load data, it takes historical weather data, and it finds the relationship between weather and load. And from there, we can find, then later we can replicate load forecasts. And because we have this stochastic process that characterizes the error in this load, we can get probabilistic forecasts. And the same thing for the solar production, another machine learning model that will relate historical weather with historical solar production from these PV facilities. So once you take a probabilistic weather forecast, and how do you take a probabilistic weather forecast? Well, we know we make mistakes in forecasting weather. So if we take one forecast, that is the one given to us, for example, from open weather maps, since this is for all open, you take that, and we know there is an error, that we have learned this error from the past. So any combination of this one single forecast with all these errors gives us an ensemble of forecasts, and that's the probabilistic weather forecast. You pass that through the load model that I told you how we fit in the last slide. You pass that to the PV model, and then You take random draws of the load forecast error and get your load probabilistic forecast. And you also take random draws of your solar production forecast error, and you get your PV probabilistic forecast. Okay? And then there is another piece very important that we are still trying to implement, and is, of course, we have uncertainty on what is the electricity demand going to be. We don't know how much solar we're going to have, but we also don't know what is the performance of all these assets we have in the grid. And for this, we have fitted a Markov chain Monte Carlo model that will change given the weather. So for each of these little bubbles is, okay, I am here in a failure mode. What is the probability that I can go to failure mode A or operating mode A, given that right now we have this temperature and this humidity and this pressure and these wind speeds, etc. And for that, we need models that hasn't been collected. For example, for solar panels, NERC only required collecting this data starting in 2021 or 2022, so it's not data that we have, but all these great things that are coming from AI are going to help us have a better model here. What we have here is still very rudimentary. But we can get a probabilistic forecast of outages and the ratings or underperformance, if you want to call these the ratings. What our probabilistic forecasts look like, so NREL calls probabilistic forecast these bands, right? Like so percentiles. So it's like the upper forecast and the lower forecast. For us, that's not probabilistic forecast. We are showing you the percentiles, but if you could look closer, you could see that there are lines in there, right? They go up and down, so there is not such a thing as the high load forecast. There is a load forecast that for some hours will be very high, the highest of everything that can happen, and for other hours will be the lowest. And that's what we want because we really care about these variations, because our ramping capability in this system is something very constraining, given by the fact that we have a lot of a lot of nuclear power. 50% of our electricity coming from nuclear power in a system like Duke Energy Carolinas, Duke Energy Progress. So here is, like, for example, this a net load forecast. We look at load separately for PV, but I mentioned net load forecast because this is an approach that we proved during the summer competing in a net load competition. Unfortunately, we were all on vacation for the first 3 weeks, so our performance wasn't great. But in the fourth week, we would have won the first prize if we had this implemented. And then we can generate many, many scenarios, and this is another place where we can use machine learning. How do we just, out of those several, like hundreds of scenarios, how do we get just a small set that is more tractable and we can input into our models? So here is, like you can see at the top, we have tons of them, and then at the bottom, we just have a few that represent the uncertainty, but they are fewer and more tractable. So as I said, our industry partner is Duke Energy. It has a large capacity from gas, as you can see here, a large important capacity from nuclear, and a lot of capacity from solar. This is really impressive, 6 gigawatts of solar, which generated like almost 7% of US solar capacity. And then if you look at the generation, 52% from nuclear and almost a third from gas, but non-negligible generation from solar, 6 terawatts of solar, which is also impressive. And then these 2 gigawatts of pumped hydro storage, that is what allows us to have all these renewables with a kind of inflexible system, because a nuclear plant cannot wrap up and down, cannot be shut down, etc. Okay, so we have our forecasts are characterized, and we have this system, right? So this is a software that will simulate, okay, what is my plan for starting and shutting down plants, and then every hour, what should I do now, adjusting the generation hour by hour. This is what Duke Energy has. They run a balancing unit commitment, and we replace it with a risk-adjusted unit commitment. And I'm going to show you what risk-adjusted means. So risk-adjusted means that we take the expected value of cost and risk. So we're going to take an average, a weighted average of the expected cost of meeting demand plus the risk of exceeding that cost or having a cost that goes away with, like, that is required for running these plants. So we weight the expected cost and the risk, like you could say, like the return on the risk, by a risk aversion coefficient. And then we have the normal constraints. For example, we have to make sure that we never generate less than what is the minimum possible generation in a power plant or more than its capacity, that if we have a plant off, then we don't ask it to generate electricity, that it is on, we keep it online for a set number of hours as required, that it cannot ramp up and down outside of its capabilities. And so we account for these costs and constraints in the decisions we make right now, which is the first stages, or the decisions that we are planning to make later, which is the second stage. And so this is a many constraints because we have to do it for all the units and all the time periods and for all the scenarios and all the time periods, because this expected value is calculated across our probabilistic forecast, right? So we are saying, what is my expected cost? Is the cost under this scenario multiplied by this probability of this scenario plus the cost of this other scenario multiplied by this probability of this other scenario, so on. So we are calculating this expected value over the probabilistic forecast. We have decision variables for every single scenario, and that grows very quickly. So if we took just one case, for example, and actually, so this, we just took load and generation data, and we put them together, we reduce the set, we can see that we get improvements. So the improvements are not going to be 10%, 20%, they are going to be around 1%. And this is still very impressive because 2019, we're doing it for a historical actual of 2019. 2020 was weird with the pandemic. 2021 was still weird. 2022 wasn't available when we started this. So this is 2019, a year with no blackouts, no cold spells, and still, and Duke Energy had a fantastic forecast, and still we can improve costs, reduce costs by almost 1%, and we can also reduce emissions. We can reduce CO2 emissions, we can reduce NOx emissions, we can reduce SO2 emissions. And then if we consider, okay, let's not look at 2019, but 250 possible 2019s that could have been different, then we could see that they could be 2% lower for this 2019 fleet. Now, let me, and we would have, where does these gains come? They come from differences in how we use the storage, which is a very critical asset here, and how we reduce the cost, the fixed and operating cost. But then let me just say the last part, which is the third part I told you is the libraries of solutions, okay? Why do we need libraries of solutions? So here we have, I'm just showing you a table of cases in which we have 12 scenarios to characterize the uncertainty, or 20, or 25, or 50. The more scenarios we have, kind of the better, because we are encompassing more of the uncertainty. But the more scenarios, the larger the number of binary variables, the larger, and the larger the number of constraints. However, some of these binary variables are always 1 or 0. So Mauricio has looked a lot about these, and then he has said, okay, if they are always 1 or 0, let's just fix them, and let's learn from these solutions. Let's keep the solutions in a library, let's learn about them, and then we will solve the problem faster. So we're going to set the commitment for those power plants, not as decision variables, but as inputs. You can also see the constraints, so many constraints, and they grow. So for the 50 scenario case, we have 10 million constraints, more than 10 million constraints. But some of them are never binding. There is not a problem with ramping up and down sometimes at night. So we are also learning which constraints to eliminate. So I have no time to show you those because I don't want to exceed my time, to be respectful to the, but we have, I'm just gonna go very quickly and keep this, yes. But there is more we can show, is particular the machine learning applications are, you can ask Kyle, who is our machine learning expert, and Mauricio, who's done all these work to find this algorithm that searches the libraries in the best possible way to solve a complex problem faster without sacrificing any of its optimality. Okay, with that, thank you.